All right, so guys, I started telling you a tiny little bit in class about this next subject that we're going to be doing, which was concavity. And it's basically the way that a graph bends. And so we've got this function x cubed that I put on here, this crazy picture that's got a lot of stuff going on, so I'm going to try to explain it as we're going. So the function y equals x cubed, it rises the entire time. It's increasing the entire time. But what we see is that it's rising in a different way. Like here, it's rising, but it's kind of slowing down as it goes. Here, it's rising, but it's getting steeper as it goes. And so the concavity has to do with the way that the graph bends or the way that a graph curves. And so we're looking at these different lines. If you look at the tangent lines, what's most important on the left is the tangent lines on the left-hand side are getting less and less steep. That's the mark of a concave down shape. And then if you're looking at the ones on the right, the tangent lines get more and more steep, and that's the mark of a concave up graph. So this piece right here, and we've already got the words, the curve y equals x cubed is concave down from negative infinity to 0. And like I said, we already have the phrases just down below. And then it is concave up from 0 to infinity. Okay, so two different pieces. It's the way that the graph bends. So this is what I was just telling you. What do you notice about the tangent lines when the curve is concave down? And this is something, one thing that I pointed out is that the tangent lines are constantly getting less and less steep. But another thing that I want you to notice is that if you're looking at the graph, and it's kind of hard to see which one is the graph, so I'm going to emphasize it here. This is the curve itself, and then there it goes. Whoops, right there. Okay, so one thing that's important about these tangent lines compared to these tangent lines is that these tangent lines are always above the curve. These tangent lines are always below the curve. That's another really important mark of being concave down versus being concave up. Any graph that's concave down, all of its tangent lines will always be up above. And so because of that, if you were using the tangent line to approximate something, your value is always just slightly above the actual graph, and so any estimate would be an overestimate. And that's because the tangent line is just slightly above the graph. If you get farther away from the point, of course, it actually intersects the graph at a certain point. What do you notice about the tangent lines when the curve is concave up? We already mentioned this as well. All of the tangent lines are below the curve. And so if the tangent line is below the curve, then any estimate that you try to make would be a slight underestimate. The tangent line values are all below the values on the actual curve. Okay, that will come into play during a lot of AP tests, so we'll talk more and more about that throughout the year. So concavity. I've already said this a couple of times, and I think I mentioned it to you guys in class, but the simplest definition I can give you, and it gives you a really nice visual, concavity is the way a graph bends. Okay, so the graph of a differentiable function, important, always important, is concave up if y prime is increasing. And so that's what we are looking at on the right-hand side of this picture right here. You can see that the derivatives are increasing as we go. Okay, so as we move, like here's a tangent line. The tangent lines get steeper and steeper and steeper as we move up this graph. So we can say that y prime is increasing on this particular interval. And then if we look at the concave down shape, the exact opposite thing is happening. As we move from left to right, these slopes are actually decreasing. The tangent lines are getting less and less steep. So concave down means the derivatives are decreasing as you move. Okay, so concavity test, something that we're going to get to. We're going to start to talk about the shape of the graph. We already did increasing and decreasing. We did maxes and mins. We will, of course, continue to talk about those while we pull in every little detail about a graph. But the concavity test is going to tell us whether something is concave up or concave down. And so when we're looking at y prime, if y prime is increasing, I'm going to say this slowly, if y prime is increasing, that means its derivative is positive. So the derivative of y prime is positive. The derivative of y prime is y double prime. So that is what we are writing down here. The graph of a twice differentiable function is concave up where f double prime of x is positive. And again, that's the same thing as saying that y prime is increasing. If y prime is increasing, its derivative is positive. The derivative of y prime is y double prime. So we could write f double prime, we could write y double prime, either way. And then it's concave down where f double prime is negative. Okay, same thing. If y prime is decreasing, its derivative is negative. So y double prime is negative. So two different ways to look at it. You can either consider the derivative to be increasing, or you can consider the second derivative to be positive. Same thing here. You can consider the derivative to be increasing, or you can consider the derivative to be negative. All right, so we are going to use that concavity test a couple of times on the next page. Look at a couple of samples here. So use the concavity test to determine the concavity of given functions on the given intervals. So we want to know, when is a function concave up? When is a function concave down? Because as you can see from the graph that we were looking at on the previous page, it's not always one concavity. A lot of times you'll switch concavity, just like graphs switch from increasing to decreasing. So x squared on the interval from 3 to 10. So we're going to start with the derivative. So the derivative is y prime. Y prime is 2x. The concavity test has to do with the second derivative, but of course you can't find the second derivative without finding the first derivative. The second derivative is 2. So we want to know whether the second derivative is positive or negative. Well, the second derivative is 2. That means the second derivative is always positive. So y double prime is always positive. So what that means is that y equals x squared, our function, is always concave up. And I think we probably know that if we think about what this graph looks like. So if we're looking at this graph right here, we know what a parabola looks like. And we should recognize what the concave up shape looks like. Remember I gave you the visual of that ruler? If you bend a ruler up, it would look like this shape the entire time. If you bend a ruler down, it would look like that. So x squared is always concave up. When we find the second derivative, we find that it's always positive. So the concavity test kind of proves what we already knew about that normal parabola. Okay, next, we want the first derivative, then we want the second derivative. So the derivative of 3 is just 0. The derivative of sine is cosine. And then the derivative of cosine is negative sine. Okay, so that is the second derivative. We want to know when that derivative is going to be equal to 0. That's kind of our first start. It's a very similar process to finding out when a function is increasing versus when a function is decreasing. In order to find when the the second derivative, in order to find when the second derivative is positive versus when it's negative, we first need to find when it's 0. And then we set up a sign chart. It splits everything up into different pieces. And so we have all these different pieces. We want to see when is the second derivative positive, when is the second derivative negative. And so we split everything up using a sign chart. All right, so we want to figure out where exactly the second derivative is going to be equal to 0. So sine of x, we can divide out that negative. And so we just want to know when sine x is equal to 0. And so x is going to be equal to 0, at pi, at 2 pi. They gave us this restriction though, and so we're going to mark the ends with 0 and 2 pi. And then pi right in the middle is really the only time where the sign could change. So this right here tells us when the second derivative is 0. That is the only place where it's 0 on this interval. And so in this interval, it's either entirely positive or entirely negative. And in this interval, it's either entirely positive or entirely negative. So this is a sign chart for y double prime. I warned you guys the last couple days that we need to start marking our sign charts because sometimes they'll be for y prime, sometimes they'll be for y double prime, etc. So this one right here, we are going to test out this sign right here, the sign right here. So if we plug in something between 0 and pi into the second derivative. That is this one right here. So say I plug in pi over 2. Negative sine of pi over 2 ends up being a negative 1. So this comes out to be negative. Okay, this one, from pi to 2 pi. If I plug in like 3 pi over 2, the negative sine of 3 pi over 2 is a negative 1. So that comes out positive. So there's our sign chart. So what we want to know is the concavity on any given interval. So on this interval right here, y is concave down. So here's what we're going to write. And we're going to write our AP explanations too. So you might want to write small. So y is concave down on the interval from 0 to pi. And that's because the second derivative is negative. And then the second interval, y is concave up on the interval from pi to 2 pi for the exact opposite reason, because y double prime is positive there. So just like the AP explanations we were practicing with increasing or decreasing or maxes or mins, this is really all you need to say, is you just state the sign of the second derivative as a reason for an interval being concave up or concave down. Okay, another definition here. The point of inflection is the point where the concavity changes. All right, so the point of inflection, this is a point where the concavity changes. Okay, so how do we look for points of inflection? Well, we look for points of inflection by finding where y double prime is equal to 0 or is undefined. Now, they don't all turn out to be points of inflection. They may or may not turn out to be points of inflection. So I actually usually call them potential points of inflection, because until we check a sign chart like this, we don't actually know if the concavity changes, just like we don't know if a critical point actually ends up being a max or a min. All right, so find all points of inflection on the graph of this function right here. So we start by taking the second derivative. So of course that starts by taking the first derivative. So this is going to be a chain rule because I've got a little nested function here. So the derivative of e to the x is e to the x. I leave my nested function in place, and then I multiply by the derivative of my nested function. Okay, so let's clean this up a little bit. Okay, so there's the first derivative. Second derivative is going to require a product rule because I have two different pieces here. All right, so let's do a little work off to the side. First function is a negative 2x. Its derivative is just a negative 2. Second function is an e to the negative x squared, and we just found that derivative. It is a negative 2x e to the negative x squared. Okay, so we're going to need that for our second derivative. So y double prime, we do u times v prime. So the negative 2x times negative 2x gives me a 4x squared times e to the negative x squared. And then plus, then I multiply these two together, and I have a negative 2e to the negative x squared. All right, so that is my second derivative. I want to find when the second derivative is equal to 0. Okay, so what I'm going to do with this is you can actually factor out that e to the negative x squared. It'll make things a lot easier on us. And then we are left with a 4x squared minus 2. And when we set that equal to 0, we do a little bit of algebra. We can set this thing equal to 0. We can set this thing equal to 0. When we set this thing equal to 0, there are no answers. An exponential function will never be equal to 0. No matter what exponent you plug in, you're never going to get an answer of 0. So we just have to worry about setting this one equal to 0. So add 2 to both sides, divide by 4. We end up with x squared equals 1/2. And so we end up with x equals plus or minus square root of 1/2. Okay, so we're going to use that to set up a sign chart, because these are our potential inflection points. Okay, I will label them potential inflection points. I need to actually set up a sign chart to figure out if they turn out to be inflection points. Okay, so here is the negative square root of 1/2. Here is the positive square root of 1/2. So let's start by testing 0, because that's pretty easy. So if I plug 0 into this function right here, this exponential piece, always positive no matter what. All right, so if I plug something in, when I plug something in, I'm really only worried about plugging it in here. So if I plug in something smaller than the negative square root of 1/2, maybe like negative 1, if I plug a negative 1 in here, I get something positive. If I plug 0 in here, I get something negative. And if I plug like positive 1 in here, I get something positive. So I'll repeat what I said a moment ago. This exponential function is always positive. Picture an exponential curve. It's always above the x-axis. So I'm really only worried about the sign of this thing right here. So my points of inflection, they occur at, I guess I can compact them, plus or minus. There we go. I've got 2 of them because the concavity does change. My graph is concave up, then down, then up. All right, example 3. The graph of the derivative is shown, so make sure that we know that. Maybe you want to throw a label on there. Answer each question and justify your answer. All right, this stuff is very, very, very important. So on which intervals is f increasing? We already talked about this. We talked about when f is increasing, when f is decreasing. So f is increasing wherever f prime is positive. And that happens all along here, and then it's negative. We need to actually exclude this point right here because it's equal to 0. It's not positive. So we write the interval from -4 to -2, and then we exclude the -2 and go up to 1. And the reason is because f prime is greater than 0 on those intervals. The graph of f prime is positive there. Okay? When is f concave up? Well, f is concave up, as we wrote on the previous page. F is concave up whenever y prime is decreasing. Okay? F is concave up whenever y prime is increasing. So y prime is increasing starting here and then just up to 4. And then we also have a point right here. So concave up from -2 to 0, that's this little part right here, and then from 3 to 4. And again, the reason is because f prime is increasing. Oops, that's not even on the page, sorry. Okay, so then we have 2 more. Again, very important questions on the next page. So we flip here. At which x coordinates does f have relative extrema? Okay, so this is, again, same graph. I just put it on the page so we can see it again. Relative extrema, that happens whenever I have a sign change of f prime, which happens right here. And then it might happen at a couple of other points, but we're not really super sure. So we're just going to talk about this one. X equals 1 is a relative max because f prime changes from positive to negative there. Okay, and then last one, this is an important one too. What are the x coordinates of the inflection points? Well, inflection points happen whenever f prime changes from increasing to decreasing, because that's when the concavity changes. So again, whenever f prime changes from increasing to decreasing, that happens here, here, and here. So when f is decreasing, when f prime is decreasing, f is concave down. Then when f prime is increasing, f is concave up, decreasing, and f is concave down, f prime is increasing, and f is concave up. So this is going to happen at x equals -2, 0, and 3. And that is because f prime, we can write it really concisely, because f prime changes direction. That's the same as saying that it changes from increasing to decreasing or vice versa. All right, we're going to skip this one for now, just because I don't want the video to go over. We're going to jump down to the second derivative test for relative extrema. We will go over example 4 together. So second derivative test. If f prime is 0, so that means we've got a critical point, and if f double prime is less than 0. First of all, this part right here, this means our graph is concave down, so it looks like this. If you've got a concave down shape, any extrema you have is going to be a max, like this. Okay, and then the exact opposite logic for the next one. If we have a critical point and the second derivative is positive, again, if the second derivative is positive, I'm looking at a concave up shape, like this. Any extrema we have on that shape will be a minimum. Okay, and then if the second derivative is 0 or undefined, then the test fails. Very useful. If that happens, which it will, and we'll talk about it when it happens, you just go back and do the first derivative test where you do a sign chart and see if the sign changes from positive to negative or vice versa. Okay, one last example, second derivative test to find all the relative extrema. So first we find critical points. These are all the places the relative extrema might occur. So we find f prime, 3x squared minus 12. Okay, and so we set that equal to 0, divide out a 3. And so our critical points happen at plus or minus 2. Okay, so those are all the points where we might have a relative extrema. We're going to use the second derivative test. So the second derivative, which is the derivative of this, is 6x. So what we want to know is the sign of the second derivative at these two critical points. So f double prime of 2. When I plug 2 into the second derivative, I get 12. What that means is that around this point, my graph is concave up. So at a point where my first derivative is 0, that means I'd have a min. Here, if I plug in a negative 2 into the second derivative, my second derivative is negative 12 there. That means my graph is concave down, so any extrema I get would be a max. So x equals negative 2 is a relative max. Because the second derivative is negative. It seems counterintuitive. It seems like a max should go with something positive, but again, just visualize what the graph looks like. And x equals 2 is a relative min. Exact opposite answer, because f double prime is greater than 0. All right, so that is it, I think, I hope. Yep. All right, so we will do this problem together, and we'll work on some problems in class.